Hello everyone, and welcome to today's workshop on climate change for the Copernicus WEkEO service. So my name is Gaëlle Sterbik, and I'm a training officer at Mercator Option International, and I'll be your host for today. So over the course of this training, we will explore key aspects of the WEkEO platform and its data. And on today's session, we will tell you about what the WEkEO service is about and what sort of data and products you can find and what sort of application you can do with it. So before we start, let's quickly go over some house rules and guidelines to make sure you enjoy this webinar. So first, we ask you not to use the chat that you see on your right-hand side for your question. You can use it for small talk or to say hello to us, but if you have a more technical question or content-related question, we invite you to use the dedicated Q&A section that you will find. That you will find on the website. So you will see the Q&A section, on the top bar, and simply click on it to open the dedicated space, and that's where you can ask our speakers your question. And while you're there, you will also see a quick survey about this training workshop. So feel free to fill it out anytime during the session. Concerning the agenda of today, so we will have many interesting presentations, and we will start with an introduction to the WEkEO service by me, and then we will have a presentation of the Copernicus Climate Change Monitoring Service by Chris Stewart from the European Center for Medium Range Weather Forecasts. And after that, Annalena Erdmann from EUMETSAT will present to us some WEkEO tools. So the graphic processing unit and the WEkEO tool Earthkit, which is an open source Python development led by UCMWF for speeding up weather and climate science workflows. And then after a short break, we will have 3 presentations about specific application of these Copernicus products. So we will have Javier Coronio from the Polytechnic University of Valencia in Spain. Then we will have Inés Giro and Ana Oliveira from Collab Atlantic based in Portugal. And finally, Davide Faranda from the Climate and Environment Science Laboratory in France. So now let's dive into a small introduction of WEkEO and Copernicus. So for those of you who don't know, Copernicus is the Earth observation component of the European Union Space Program, dedicated to monitoring our planet and its environment. So it provides free and openly accessible information services based on satellite observations and in-situ data, helping service providers, public authorities, and organizations to improve quality of life in Europe and beyond. And Copernicus operates through space-based and in-situ observation components and offers dedicated information service through self-standing portals tailored to various user community. So Copernicus offers a lot of valuable environmental data across its various services, and WEkEO has been designed to bring all of this information together in one convenient place. So instead of navigating multiple platforms like the Copernicus Marine Service or the Copernicus Atmosphere Monitoring Service, you can access on WEkEO all of the original data from all of the Copernicus services and Sentinel missions directly through the platform. So whether your focus is on marine, land, atmosphere, or climate data, the platform provides a unified and efficient environment to explore and work with these datasets. Next. Sorry, my computer is a bit slow. And then, so with WEkEO, getting started is quite simple. You don't need any registration to view, explore, and discover the right range of available data. Everything is open for you to browse freely. And if you'd like to take advantage of more advanced features, you can create a free account to access personal working environments where you can organize and manage projects, cloud resources, and advanced tools. Okay, and then concerning this slide, so WEkEO gives you access to over 400 data sets from Sentinel missions and the Copernicus atmosphere, climate, land, and ocean services. And to help you explore this data, two tools are available. So the Expert Data Viewer, which provides a detailed interface for dataset visualization, and the new Light Data Viewer designed for faster and simpler visualizations. So we'll explore the Expert Data Viewer during our second day of this webinar. Then we have the Jupyter Catalog. So it's a Jupyter Notebook gallery with over 100 ready-to-use notebooks developed across the Copernicus services. You can view notebooks directly, clone them via GitLab to customize for your needs, or launch them in the WEkEO Jupyter Hub if you are a registered user. So this growing collection of notebooks covers a large range of topics and workflows to help you learn and apply best practice when working with Copernicus data. Then you also have the WEkEO workspace, so which was formerly known as the WEkEO Jupyter Hub, which goes beyond just Jupyter Notebook, offering the full Jupyter Lab environment where you can explore data, perform basic analysis, and follow interactive workflows. It is suitable for everyone, so from beginners to advanced users, and includes access to Jupyter Lab, RStudio, and the Xcube viewer for visualizing data cubes. And for this, the access requires a registered WEkEO account. You also have the WEkEO Drive, which provides registered users with secure online storage to save, manage, and share their work directly within the platform. And this feature supports seamless collaboration and easy access to files used or generated in the WEkEO workspace. You also have a set of advanced tools designed to help you scale up your data access and make your workflows more efficient and effective. These tools are particularly useful if you're working with large data sets, running complex analysis, or looking for ways to simplify data handling and processing directly in the cloud. So these tools include the Harmonized Data Access API and the WEkEO tools Earthkit and YoCanvas. And finally, for users with advanced data processing needs, WEkEO offers scalable cloud computing resources designed to support both research activities and operational workloads. So these resources fall into two main categories to match different user profiles and project requirements. I will not go into much more details, but feel free to look on the website if you have more questions about this option. And finally, WEkEO offers dedicated expert support to help you make the most of the platform. So whether you're just getting started or tackling more advanced tasks, you will find a comprehensive help center with over 50 detailed articles covering a large range of topics. So you can also get instant assistance by asking questions to our AI agent, or chat directly with a member of the support team through the live chat widget. So easily accessible at the bottom right corner of every page on the website. And that's it for me for today. So if you have any questions, don't hesitate to ask them on the Q&A session. And now I invite our first speaker, Chris Stewart from UCMWF, to present the Copernicus Climate Change Monitoring Service. Hi, Chris.
Hi, thanks, Gail. So I'm now going to share my presentation. And yes, I'm going to give an introduction to the Copernicus Climate Change Service. So what I'll do, first of all, is just to share my PPT. Can you see it okay? Just need to put it into presentation mode. Okay, and then I just need to switch the presenter and the slideshow view. Can you see it in presentation mode?
Yeah, it's okay now. Thanks.
Perfect. Okay, great. So the Copernicus Climate Change Service is one of the 6 Copernicus services. And the purpose is to provide authoritative information on the past, present, and future climate to support mitigation and adaptation by policymakers, also private businesses, and anyone, basically. So the data is completely free. The products and the tools, all completely free. And what you see in this slide is a kind of timeline of the products that we have available. So we provide observational data going back quite far back in time. Then we've got reanalysis products. So basically, reanalysis is like observations, but it fills the gap in space and time of the observations with the latest state-of-the-art forecasting model. Okay, but it's the same forecasting model applied across the entire time series. So what you have is a very nice data set to enable you to analyze past trends in across different climate variables. So those are the data sets we have of the past climate. Then we also have products referring to the future, so seasonal forecasts and decadal predictions. And then, so that's for, seasonal forecast for the next season. And then climate projections going up to basically the end of the century, projecting how the climate may look across different variables according to different scenarios. So in the next slides, I'm going to talk about each of the types of products. So grouping them into the different climate data types, so starting with observations. So what you see in this figure is the essential climate variables. So these are variables as defined by the Global Climate Observing System that really characterize the climate. And you can see they're grouped into different, variables of the surface, of the atmosphere, hydrosphere, the cryosphere, and so on. So these are variables that can be measured and that accurately describe the state of the climate. And in this slide here, you see a set of climate data records of essential climate variables. So these climate data records are basically time series of essential climate variables going far enough back in time to be able to really characterize the variability and trends across different variables. So these are all available through C3S and of course WEkEO. And in terms of observational data, it's not just satellite data, also in situ observations we make available. So these are point observations over the surface, over the upper air, from ozone sondes, radio sondes, and so on, but also gridded observations from different in situ networks. And in addition to this data, we also have this data rescue service. So basically, the data rescue service facilitates and coordinates the rescue of weather and climate data from all over the world, from different sources. So from old ship logs, for example, that are not digitized. And through our online portal, we collect and share this information and feed it into international repositories, that promote tools, best practice and standards for all aspects of this rescue process. In this figure here, this is actually quite a cool animation that shows the importance of in situ data. So if you look at the date that's iterating over the different years from 1940. Okay, so obviously from the 1940s, we didn't have any satellite data. So the in situ data was absolutely crucial to understanding the past climate. So this is an animation of the input used in the reanalysis data that starts long before the satellite era. So now leaving observations and going into reanalysis. So the Copernicus Climate Change Service provides different reanalysis products. So basically reanalysis is like the flagship product of C3S because we're using the observation data, but also the forecast model that ECMWF provides. And we're using that to really provide a very nice, consistent data set of the past decades. So different reanalysis products include ERA 5. So that's the main global reanalysis, 30-kilometer resolution hourly and at different levels of the atmosphere. We also have a slightly higher resolution, 9 kilometers over the land. And then we also have the regional reanalysis. So these are high resolution over certain regions. So these are kind of downscaled high resolution reanalysis. And we have that over Europe and over the Arctic. And this is just a figure showing some visualizations of this reanalysis data set. So you can see they're gridded, they don't have any gaps. And also, yeah, you can see the difference in resolution, for example, between the Arctic, the regional Arctic reanalysis, the CARA and ERA 5. So the Arctic is the fastest warming region on the planet. And actually, this figure here shows a really how accurate this data is and what you can do with it. So the figure on the top is a time series going from 1950 to pretty much to the present. And it's at different layers of the atmosphere. So starting from 1,000 hectopascals from the surface to the upper atmosphere. But each point on this figure is just one global average temperature. Okay, so it's global average temperature. It's just one measurement for the whole world. And despite that, this is an aggregation for the whole world, you can still see blips corresponding to certain events. So, for example, these big volcanic eruptions, okay, you can actually see a blip in the global average temperature caused by these big events. So this just, this shows how accurate this data is. And of course, it's not just the single figure for the global average. We also, we have a gridded data set over the whole world. So in addition to these core reanalysis data sets, we also have some value-added data to support different sectors. So for example, for the agriculture sector, we have indicators useful for stakeholders in agriculture. Things like relative humidity at specific times of day relevant to the crop season. And we also have them for energy and other similar data sets. Now, I've also included a kind of grouping for climate intelligence. So before talking about climate predictions and projections, I just want to say a few words about climate intelligence. So what we do here is we collect all the data and we analyze it. We provide monthly bulletins, also the annual European State of the Climate, and we support media outlets. We provide nice visualizations, and you can really see the media impact across the years that's massively increasing. So there's a lot more visibility now, and the trend seems set to continue. This is an example of a nice animation just showing, well, actually a nice animation of a not so nice message, basically showing the time series of global surface air temperature anomalies. And you can really see that 2023 was way above average. Also 2024 was a new record, but the 2023, you can really see what a marked difference it was compared to the past. So these figures are available on the website, figures, animations, and bulletins. So the monthly bulletin, and this is a little video of the European State of the Climate. So this year it was done together with WMO, and it's characterized, it's providing a summary of the key events over the last year in Europe and the Arctic. And yeah, all of this is available as a bulletin, also in figures. So I'd suggest having a look at this in more detail. We also provide tools, so not just data, but also applications to facilitate exploration of this data. So those who do not want to download a lengthy time series, calculate the climatology, calculate the anomalies with respect to the climatology. You have a lot of data to collect. Here you have an application where you can just see the climatology. You can zoom in, you can click on a point, see the time series. It's a much more user-friendly way to explore this data. So that's also part of our kind of climate intelligence activities. Now, going on to the data sets of the future, so predictions and projections. So C3S makes available seasonal forecasts, and this is from a multi-model system. So it's not just ECMWF providing these forecasts, but different data providers. And we also provide the ensemble of all these different providers. Or you make the data available graphically, well, as numerical data, of course, but also in graphical charts and time series, and also as verification data. So if you want to see the scores of the predictions. Then going further ahead in time, so climate projections. So these are projections of the future climate according to different scenarios. We make available, so basically we're brokering this data. We're not doing it ourselves, but we're making it available. So this data is also available on the Earth System Grid Federation, on ESGF, but through C3S, it's a little bit more user-friendly. It comes with quality control, with data tutorials, with a seamless kind of data access system, because there are many different models provided by different people. So it's useful to have a unified portal where you can access this data in a kind of user-friendly way. So through WEkEO, of course, you can get this data. You can get the data for the global climate projections, so CMIP 5, CMIP 6, and also for the regional climate projections. So these are kind of downscaled climate projections, high resolution over a particular region. And these are the Cordex regions, the Cordex regional climate projections. So similarly, we have an app to help you explore this data. So this is called the Climate Atlas. So the Climate Atlas is, well, you can do even more than the previous one I showed, Climate Pulse. So this one allows you to explore many different variables from reanalysis data, from climate projections. And yeah, again, you can zoom in, you can click on certain points, you can look at climatologies, anomalies, various different trends. And you can really play around and explore different scenarios. So yeah, so this is a very nice user-friendly tool. A few slides on user support, quality assurance, and training. So C3S is an operational service. It doesn't just provide data for researchers to do, without any kind of support. We do provide, a lot of operational support. And one of the things I'd like to mention is the evaluation and quality control. So the data sets have gone through a rigorous quality control process to ensure that they're fit for purpose, to identify what the purpose is and to communicate that to users. And also to make sure that there's uncertainty information, that the metadata is clearly there, that there's good documentation, and any issues are flagged and addressed. So, so this is one big component of C3S. So, of course, you have the WEkEO user support. We also have user support at the service level of C3S. So there you can find information on documentation and how to raise a ticket and so on. And of course, you provide a lot of learning resources integrated with WEkEO. So on the WEkEO Jupyter Hub, you will find Jupyter notebooks showing you how to explore this data. In addition to Jupyter notebooks, we also have e-learning modules and explainer videos that are available. So I'd recommend exploring these resources. And then I know that Earthkit is going to be presented also by Annalena, just mentioning very briefly here that this is an open source package to process climate data. It's basically a wrapper for X-Array and these other libraries like Matplotlib and Cartopy and so on. There are different packages, and it's really a convenient way to explore the climate data in Python. So we have some tutorials showing examples of how to apply Earthkit for different processing routines. So just to summarize, the Copernicus Climate Change Service is a recognized global voice on climate, informing EU institutions, but also the IPCC and UN institutions and public and private organizations throughout Europe and beyond. It's truly a European effort with offices in various different countries. So we have Bonn, we have also Reading in the UK, and we have Bologna, where the data center is in Italy. But we also have contracts and agreements with every EU member state and all Copernicus contributing countries. We're really informing the global discourse on climate through products that have become so well used and relied upon. It's really a common resource for many organizations, including media outlets, public and private organizations. So it's a trusted, authoritative, and operational source of information on climate for everyone, pretty much. And with that, I finish my presentation, and hopefully there are some time for questions. So let me just...
Thanks a lot for your presentation, Chris.
And I'll stop sharing.
And so we have a few questions. So we will start with the first one being about the Climate Atlas. So is the Climate Atlas like a viewer, or does it work differently?
Yeah, so the Climate Atlas, is like a viewer. And what it enables you to do is to view the data. So you can visualize it. You can visualize it in as a spinning globe. You can zoom in, you can click on a particular grid. And then for that grid, you can then expand another dimension. You can see the time series. So it's basically a graphical user interface for exploring the data to save you from having to download all the data and process it by hand.
Okay, thanks a lot. A question about the catalog. Have you already included data from the new Earthkit satellite level 1 products? Oh, okay.
No, okay. So I don't know to what extent these have been assimilated already into the products. I can try and find out and get back to you.
Okay.
But at some point they will be assimilated. Yeah.
Okay. Thanks a lot. This question, isn't ECMWF in charge of the Copernicus Atmosphere Service also? How do you handle both services?
Yeah, it is, exactly. So ECMWF is the entrusted entity for both C3S and CAMS, so the CAMS being the Copernicus Atmosphere Monitoring Service, relying on ECMWF's expertise in forecasting. So it's logical that we handle, that service as well. So CAMS provides more kind of forecast data, so over shorter timescales. So we provide forecasts over the next 4 or 5 days. So 4 days for the European air quality forecast, 5 days for the global atmospheric composition forecast. We also provide reanalysis data, but reanalysis data for atmospheric composition. So different chemical species and aerosols. So yes, similar products, but different timescales, not so much climate, it's more on the short-term forecasting, and it's more focused on atmospheric composition. Yeah.
Okay, thanks a lot. Next question. Can the data be cleaned, manipulated, or visualized using MATLAB with the tools you're using for local or regional climate projection analysis?
So you can use MATLAB, of course. The data come in GRIB or NetCDF formats. So, of course, you can use MATLAB for doing this kind of data analysis. We have tutorials in Python. We don't have so much support material for MATLAB, But of course, yeah, you can, if you're more familiar with MATLAB, then of course you can use that.
Okay, thanks. We also have a few questions on the model used. What kind of models do you use for projection and forecasting? And we have another one asking if the models are using a couple between ocean and atmosphere, for example.
Yeah, okay. So I'm not an expert on the models used for climate projections and or for the predictions. Just to say that we do, we have multiple models from different sources. You can find the full documentation of all those models on the data catalog. So if you click on more information, you find the full documentation. If you really want to know exactly what kind of models and the resolutions and the data providers, all that information is available.
Okay, thanks.
I hope that somewhat answers the question, or at least defers the question to where
Yeah.
it can be answered.
One question also, same type of question. What are the rules for using your data for commercial projects?
Yeah, so the data is completely free and available also for commercial projects. So you can use them, businesses can use the data as long as you cite the data properly, they can be used for commercial applications.
And yeah, I guess they also have to cite the data they used using the DY or something like that on the projects, no?
Yeah, so there are different there's a different licenses. I can't remember exactly which license, but if you look at for each product, you'll see the license, and it'll come with instructions on what the conditions are. But they can be used for free, so that's there's no doubt about that. Anyone can use them, and you can use them in for business purposes.
Thanks a lot. In the climate atlas, I can see that there is climatology available based on IPCC AR6 regions. On what basis are these regions, I think, maybe separated or decide is not country-wise?
Okay, so the climatology can be created on different regions, but also country scale, also different NUTS regions. So there are different ways to aggregate the data. The Climate Atlas provides different types of aggregations, so you can choose where you want to see the climatology, if you want to see it for a whole globe or for specific regions. It's not just the IPCC AR6. You can choose different aggregations. So yeah.
Okay, thanks. Okay, one more general question. From what I understand, for climate analysis and downloading datasets like ERA5, the CDS platform seems more suitable than WEkEO. Would you agree with that?
Okay, well, you can get the data from WEkEO. You can get the data also from the Climate Data Store. The advantage of WEkEO is that you have not just the C3S data, you also have data from other services, and you have the satellite data. So the advantage of WEkEO is that you can, for example, in the Jupyter Hub, you can get data from multiple sources and you can process all that together. Now, the actual data access mechanism, I think now it's becoming more and more similar to the CDS. There are probably still some differences. Obviously, if you go straight to the source, then maybe it's advantageous for certain applications, but the advantage of WEkEO is that you really have data from you can get multiple sources you can get data from multiple sources. So that's really the advantage of WEkEO. And of course, you've got the virtual machines if you want computing power. So yeah, I mean, you can get data from both the CDS or from WEkEO, and yeah, I mean, I think it depends on what kind of what your application is. If you're interested in using multiple data sets, then WEkEO is probably more advantageous.
Yeah, that's what I was going to say also. Thanks a lot. So a general question I think I can answer. Is there a WEkEO learning session that explains how to downscale climate data using machine learning? So at the moment, no, but it's in development. I think it will probably happen next year or something like that, using at least trying to using AI or machine learning in the tutorials we will present during the WEkEO session. So stay tuned, and it's a subject that comes back a lot, so we'll keep it in mind for the next session. Okay, I think we have time for two more questions. Is there a plan to I'm sorry, I can pronounce it, operationalize regional reanalysis SIRA as it is the case of ERA 5 land? SIRA is now available only until 2021.
Yeah, I have to get back to you on that. I'm not entirely sure what the plans are for Sarah, but I can speak to the regional reanalysis team and I can get back to you. So
Okay.
yeah.
Okay, I will put the question on the side then. And yeah, one last question before we have to move on. Does CMIP6 have any downscaled products for the whole world, like the Cordex dataset for CMIP5?
Yeah, exactly. I think the Cordex data sets are quite old now. The problem is that these climate predictions are still not considered kind of like operational products. So I don't know what the plan is, but I can try to find out and get back to you on what the plans are for
Okay,
CMIP6
thanks.
and yeah.
Okay, so yeah, I put both questions on the site for later answer. Thanks a lot, Chris. And yeah, so we have a few unanswered questions, but we will put them together in a post-event report with useful link and everything needed for you to have your answer. So don't worry if your question hasn't been answered yet. Thanks again, Chris, for your presentation and your participation. And
Many thanks.
yes, we will go now to the next presentation, which is about WEkEO tools by Annalena. And yeah, Annalena, whenever you want, you can join us and start sharing your screen. Welcome.
Hi, thank you very much for the introduction. Let me quickly share my screen. Okay, you should now be able to see it. I hope that's the case.
Yeah, it's okay now.
Okay, very good. Yeah, hi, good morning, everyone, and welcome to my part of this webinar. Thanks for inviting me. I will now guide you through two of the WEkEO tools. One is the WEkEO plugins for Earthkit, and the other tool is the GPU. My name is Annalena Erdmann, and I'm a Copernicus Data Services Engineer at EUMETSAT, and I'm, involved in WEkEO evolutions and new services. Let's start right away with the Earthkit. So Earthkit in general is a Python toolkit developed by ECMWF, and it's designed to simplify and standardize the handling of Earth system data. So especially large-scale meteorological data or climate data sets, but it can also be applied to any other kind of data, for example, satellite data or land data. It's highly modular, so you don't have that one tool, Earthkit, but it's like put together from several models. Like there is Earthkit data, which includes the data access, Earthkit plots, which has some visualization capabilities, and many, many more. I've put also the reference to the official documentation here in the slides for you to check it out later. And I would also like to point out that very, very nice presentation that was given by James Warndell in the WEkEO Essentials webinar. And he gave a full dedicated session on Earthkit and explained from ECMWF side how they developed it and what all the capabilities are. So yeah, feel free to check this out. It starts at around minute 26 of the webinar. WEkEO has contributed to the Earthkit Python package by a plugin. So WEkEO is now supported as a data source for the Earthkit data package. And so the key features are that you can, through the Earthkit syntax, seamlessly access the data which is available on WEkEO, so using the WEkEO HDA. And Earthkit hides all the complexity of data formats, of data management for you. So you can, using Earthkit, directly convert data, for example, to X-array and then go on with your processing from there. And also you can use the Earthkit plotting functions on some data sets of WEkEO. Not everything is supported, unfortunately, but I will show later a quick overview of which data sets are supported in Earthkit. There is also a lot of documentation available on how to use Earthkit with the Earthkit WEkEO plugins. And because I think it's always nice to have some interactive part, I will now show a quick demo of the Earthkit WEkEO plugin and how to visualize data with it. And with this, let me switch to my other browser window. So I am now on the WEkEO workspace. You can also go to the WEkEO workspace if you have a user account. And here in this public folder, you will find many, many example notebooks. I am showing the notebooks on how to visualize data with Earthkit, a slightly adapted version because we don't have too much time today. So we'll look at the land surface temperature data set from the Copernicus land monitoring service. And I will now quickly show you how to access the data set and how to plot it using Earthkit. We first do all the necessary imports. Here you see that we're mainly using the data, the Earthkit data package. And this is practically the most important cell because here you see how the data is downloaded. So Earthkit data has an argument which you fill in with the source where you want to get the data from. And because we have this WEkEO plugin, we can just simply say we want to get the data from WEkEO and add the request here. This request is the JSON payload you get, for example, from the viewer when you select data sets. It's the same syntax which you also use when you access the data, for example, through the WEkEO API. And then without downloading any, well, it downloads data, but it stores it in cache. So you will not see the data here on the left in your working directory, but you will be able to directly convert it to X-array. So we see we have 1 day time series with different variables like maximum land surface temperature, median, minimum, and so on. So now we have all the data in our working environment and we can just continue with our processing. The next step is to visualize the data. So I've executed the notebook a bit beforehand because the visualization, it takes some time because it's quite a large data set. It's around 300 megabytes. So actually visualizing it, it's a bit difficult. And the Earthkit plots package, it really is useful because you do not have to worry about, okay, how to add a base map, how to add like the latitudes and longitudes in your legend, but it all does that automatically. You simply have to add the area, the units, and the data which you want to plot. And then it really nicely shows the data on the plot. Here we compare two different variables. One is the minimum and one is the median, very nicely next to each other. You can also select different geographical regions. So here we now select Italy for one and Spain for the next plot. And you see with just those two keywords, we are able to get the two different plots. And also, if you want to add more plots, this is easily possible by just looping through the data set and then just making a really nice matrix with the Earthkit plots function. And this is just very, very convenient for doing processing, for doing plots, and for getting access to the data. With that, I return to my slides to give a few words about which data is supported. So the download through Earthkit is possible with almost all the data through WEkEO. 80% can be converted directly to X-array, and the plotting functions are supported with around half of the data sets. So some data sets are not supported because the projections are very, very specific, or the data format is very, very specific. So this is the case for example, some satellite data like altimetry data that is just not supported yet. And here you can see a quick overview of the different services. So for example, here a high percentage of Mercator Ocean, like the CMEMS data sets are supported with access, converting to X-array and plotting. Also the ECMWF data sets, which is kind of clear because yeah, it's originally done for the climate and meteorological data sets. Now coming to the next service, I'm very happy to introduce for the first time. These are the WEkEO workspace GPUs. WEkEO has since 2 weeks ago, so it's a very, very, very fresh service, graphical processing units on the workspace. So it's available to users who have a user account, and when you access your WEkEO workspace, you can now also access GPU processing power. There is around 8 gigabytes, I checked earlier, it's actually 7 gigabytes of GPU memory in the machine learning GPU server, and up to 5 users can use the GPUs at the same time. So what does that mean? It means if already 5 users are logged in using the GPUs and you're the 6th user, you might not be able to use it. So it's recommended to just wait a little bit, and then once one is free, you will get the access to it. You can use the GPUs on the WEkEO workspace to speed up training of small machine learning models, to prototype model training, and also to do inference on lightweight models. A few words on how to access the GPUs. So if you're here on your on the landing page and you're logged in, you can go to the My WEkEO. You click My WEkEO, and you can see here the WEkEO workspace widget. When you click on Open, then you will first have to log in with two-factor authentication. But once you've done that, you have the option to select your server. And 2 weeks ago, we added one option, which is the machine learning GPU server. And when you select this, you will see, okay, it's starting up as usual. It should not take more than 2 minutes. If it's taking a really, really long time, chances are high that it's full already. So I recommend to just try later again. And then it will redirect you to the Jupyter Hub. You will notice that it looks exactly like your usual user space. So you have all the data which you've produced in the past already, all the code. And this is really handy because it enables you to, for example, do the data preparation part in the Earth observation server and then move to the machine learning GPU server only when you really do the model training and inference part. There is one notebook available already, an introduction to the WEkEO workspace GPUs, and I will just jump over again to quickly walk you through this notebook. That you can see what you can learn here in the notebook. So it's just a very, very simple introduction to the GPUs, and tools you can use to monitor, for example, the usage. So in this notebook, you can find again when you're in your working directory. I have a really large number of files because I've been working with WEkEO a lot. In your public directory, and then when you go to WEkEO for data and the WEkEO GPU, you will find that notebook. It first introduces how to access the GPU environment that I already explained, so I can just jump over that. When you're already logged into the Jupyter Hub environment and you're not sure, is it the GPU or is it another server, you can very easily, you can just check that with NVIDIA SME. And you can see here now, yes, GPU is detected and I have 6.2 megabytes of memory available right now. Another very useful tool is NVTop. I will quickly start that, because here you can see the usage of your GPUs. And we can quickly try it out with a matrix multiplication. And hopefully when we start this multiplication, we see a spike here now in the memory and in the usage of the GPU. When we empty the cache, we should see a decrease in the usage, ideally. And yeah, there is also some code available to make a comparison of CPU and GPU runtime, which you can see is it's quite powerful. So the GPU, when it comes to matrix multiplication, it really speeds up things, and this is essential when you do and then the machine learning training. So with this being said, you're very welcome to try out the notebooks and the GPU yourself. As I said, it's available already. And if you find at one point that the GPU, like this 6 gigabytes, 7 gigabytes, which you have on the Jupyter Hub, is not enough anymore for your project, I would really want to point you out to I would like to point out to you the Copernicus Innovation Lab. That is an initiative from where you can get cloud computing resources for projects using Copernicus services and Sentinel data that benefit economy, society, and environment. So the scope is pretty broad. And projects of Copernicus users from the Copernicus member states can apply for the Innovation Lab. You can just scan the QR code here, which redirects you to the WEkEO website, and then go to the Innovation Lab section and you'll find more information here. It's a really, really nice initiative to support projects with computational resources like CPU, virtual machines, and also GPUs. And that's all from my side. Thank you very much, and I'm happy to take any questions.
Thanks a lot, Annalena, for your presentation. Okay, so I'm back. So we have a few questions for you. The first one being, in case of gridded data, can Earthkit be used for visualization?
Yes, yeah, exactly. So usually if the data is in a gridded form, like with latitude, longitude dimension, time dimension, it can be used for visualization. For example, NetCDFs with respective dimensions, they are in most cases supported for visualization. It really becomes difficult when you, for example, have imagery on an instrument grid, so only with X and Y and no time dimension and so on. So there it gets difficult, but in case of the gridded data, yeah, it's usually supported.
Okay, thanks a lot. Can matrix multiplication be used in integration with Python JetBrains Community Edition?
I am not aware of the JetBrains community, but I mean, what I can say is that the WEkEO workspace GPU just behave like any other GPU. So when you could use these JetBrains Community Edition also on a local machine which has a GPU, then yeah, I don't think anything speaks against also using it on the WEkEO workspace.
Next question, does Earthkit require someone to learn Python or Java, or does it accept code generated by AI?
Well, so Earthkit is in Python, so some knowledge of Python I'd say would not hurt. However, I mean, I have not tried out generating code for Earthkit with ChatGPT or so. It might work to a certain extent because it's quite well documented. So yeah, you can just give it a try. But I would always recommend to just yeah, learn some Python and then double check what the chatbot has given you out as code to be sure that you're doing the correct thing and also the correct processing.
Yeah, I agree also. This question, are these services hosted on European servers or on cloud-based services from non-European third-party providers?
The services like the WEkEO workspace, it's hosted on a European server. So our infrastructure provider is Cloudflare. So we are the WEkEO workspace, but also in case you're interested in the innovation lab resources, that is all hosted in Cloudflare's data centers in Warsaw.
Okay, thanks. Okay, so we have the two same question. How do we know when the GPU is available or not? And it's also the last one we see if the user gets a warning from the system to log in when the GPU is available.
Yeah, so that is a very good question. So at the moment, you will know that the GPU is not available when the server spawning fails. So you will get an error message. There is a help center article on how this error message looks like, but it's not really comprehensive on first sight. We are currently working on it that you get an error message right away. But as I said, it's 2 weeks old, so it's all work in progress. But yeah, so at the moment you'll just get a timeout error, and hopefully soon in the future you'll get a more comprehensive error message saying, okay, please try again later.
Okay, thanks. Okay, we'll mark this one as answered. This question, so in the workspace, I have chose Earth data analysis, how to switch into GPU mode.
So you can switch by, maybe I can just quickly show it in
Oh
the
yeah, go ahead.
in the because I have the
It will
Jupyter
be
and the
easier.
Hub open. Exactly. So when you're sure that you're not on a GPU server, you can just go to File and then go on the Hub control panel, and then you can stop the server.
Okay.
And if you stop the server, you can start the server, and then you have the choice again.
Okay. Thanks. Good to know.
Okay. I'll stop my screen sharing.
A question about the example you show. So in the visualization example using Earthkit, I noticed that the northern part of Europe wasn't covered. The map seemed incomplete. Is there a reason for this?
Yeah, a really good catch. So the product I'm using is from the Copernicus Lab monitoring service, and it relies on satellite data. And it just seems that that day was pretty cloudy over Northern Europe. So the gaps, they come from clouds, and yeah, this causes the gaps in the data.
Okay, thanks a lot for the explanation. This one, so nice presentation, thank you. I had a quick question about the last platform you mentioned. Is it freely accessible or does it require a paid subscription?
So the last platform, like the WEkEO workspace, that is
Yeah,
free,
yeah.
and the innovation lab, that is also free. So the WEkEO workspace, you just require a user account, so you can just use it right now if you sign up. And the innovation lab, that is like an extended offer, and you will need to like write a short proposal, what you want to do. For example, you have a research project in your university and you need one virtual machines with one GPU for 3 months of time, for doing this and this, like, I don't know, downscaling climate data with machine learning, for example. And then this proposal will be evaluated and then you will get the resources, but then it's also free. So once you're accepted in the innovation lab, then it's also free.
Okay. Okay, thanks a lot. And I think we have time for 2 more questions. So the almost last one, does Earthkit support processing curvilinear grids to rectilinear?
That I don't know. We will have to take that offline.
Okay. I will put the question on the side.
Yeah, thank you.
And the last one, can we use WEkEO GPU via an API to integrate GPU notebook execution into an external background process, then get the results, for example, as a weekly analysis?
That is a good question. So I'm also not 100% sure how that would work. Um, I mean, in the WEkEO workspace, you also have access to the command line interface, so to a terminal. So you can also use the GPU with that, so you don't have to necessarily use it in a Jupyter notebook. But I'll also check with our technical experts on that
Okay.
question, and then I'll get back to you.
I will put it on the side also if you want to have more
Yeah.
detail. Okay, thanks. So we will have to stop there for the question, but thanks again, Annalena, for your presentation and your
Okay, thank you
participation.
very much.
And yes, so for the participant, for the few unanswered questions, it will also be put on the site to be answered later. And we will be back in a few minutes after a short break for the use case testimony. So yeah, don't hesitate to take a break, look at the polls or grab a coffee, and we'll see you in a few minutes. Welcome back, everyone. So we hope you had time to enjoy the short break, and now we will go to the user testimonies, and I welcome our first speaker, Javier. So welcome, Javier, and whenever you want, you can start your presentation.
Yeah, can you hear me?
Yeah,
Fine.
we can hear you.
Okay, perfect. So, okay. Hi, everybody. This is Javier Corroño from Universidad Politécnica of Valencia, and I'm coming here to give you a short talk about the potential of Sentinel-2, Copernicus Sentinel-2 mission, to monitor methane point emissions, to actually map the emissions from, let's say, oil and gas or other sites. I will go into a bit the details of the methodology, the sites, and so on, and then I will end up with some examples and a very short example that you can do with the Copernicus browser. Very simple, but I think it shows the potential and the easy way to detect these emissions with these cloud platforms. So let me see. Okay, now it works. Okay, so what's methane mapping from space? So in the last few years, we've got several missions that are able to actually map at a high resolution, high spatial resolution, the plumes from space. We are talking about hyperspectral missions mostly. These are like ENMAP, EMIT, PRISMA, Chinese mission like GAOFEN, and others, but they are usually in the 30, 60 meters resolution, and they have a medium sensitivity. They can have a wide spatial coverage, and you can detect from 100 kilograms hour onwards emissions. So you see here that they cover basically the whole shortwave infrared, where you've got the methane transmittance, especially you've got a really strong peak in the 2300 nanometer region. But on the other side, you've got multispectral missions. These multispectral missions are not so sensitive. They have a low sensitivity, but they have 20, 30 meter resolution, and they can monitor with frequent and global coverage like Sentinel-2 and Landsat. And you can see here in the image where the Sentinel-2 and Landsat bands are in the area of the 2200, where you can find the methane absorption. On the other hand, you've got also a sensor like WorldView 3 with 3.5 meter observations, a better capacity to detect methane, but this is under payment, so they are not open for everybody. So methane mapping from space, we've got different targets. We are starting with onshore oil and gas facilities. We move into offshore oil and gas facilities. And now we are also moving into landfills. We've got examples like, for example, even the palm oil mills have been monitored for methane. And in the end, we are expanding these sites. We are moving into different areas. And this is a whole monitoring strategy that is, it includes the combination of different things. This methane mapping from space combines with inventories to reconcile inventories with methane mapping from space. They also bring auxiliary products, databases like flaring data, which is connected to methane. It's actually methane being burned. And we've got also organizations like UNEP IMEO, who is working into bringing this at a sort of operational level and trying to connect all this with political action. So going into why Sentinel-2 mission is capable of detecting methane, we've got basically two bands in the shortwave infrared, which are the band 11 and the band 12 that you can see here in the image, that respond very well to methane absorption, especially the band 12 is in an area where you've got methane absorption, whereas the band 11 has almost no methane absorption. It's got, as I was saying before, it got a very good advantage. One, the obvious, it's open. It's got a 5-day revisit, and it's got 20 meters spatial resolution. So those are very good points. The disadvantage is obvious that it's got limited sensitivity because it's not designed for this. It's got a broadband, the band 12, and obviously it doesn't respond as well as a hyperspectral mission. And usually detections, you need to be at the 1.5 or 2 tons per hour in order to start to see results. So there's a whole methane retrieval methodology that briefly I described here with this graph I show you here, where you start with a methane concentration map. that you obtain from the retrieval of the radiance bands. Then you can threshold or you can filter out the whole number of outliers that you can find in the image, and you can create a manual or semi-automatic plume mask that can be done with, as I say, manually, or you can use a machine learning process. There are several methods to do this. And then in the end, you've got a final plume mask, which you can use to actually quantify the amount of methane that is released per hour, which is the quantity that is of interest to actually understand the amount in kilograms that is released. So the methane enhancement is retrieved as a simple plots of a temporal and band ratio of the band 12 and band 11 that you've got here in the equation. We approximate this as the transmittance of the plume, and based on a relationship between the transmittance of the plume and the amount of methane, we can establish that value. This relationship can be based on here, for example, in the equation, it can be based on a simple Beer-Lambert law, or for example, in our case, we relate this with a lookup table based on relative transfer equations. So going into this ratio of bands, which is very straightforward for Sentinel-2. Other methodologies look for example, at a match filter when you've got many bands in the hyperspectral, but for Sentinel-2, because you've got only 2 bands, this is very straightforward. So you just use the ratio of the 2 bands. So basically your target band is the band 12, which is the one that detects the methane, and your reference band is the actual band 12 without that methane, the band you are going to predict. So the simple case would be to actually bring this band 12 divided by band 11. And here you've got the panels A and D, where you see the result you've got with this approach. You can see a bit in the center the emission, but not so clear. And it's as soon as we start to bring this reference of radiance reference that is not just band 11, but is a band 12, let's say, from a close date or several date, and we normalize by that, assuming always that the plumes are changing with the wind direction and are not overlaying temporally. So you can find much better results like the panels E, especially F, that you can find here. And this is a bit the whole idea, is to play with a normalization of the band 12 with the closest you've got without methane. So the idea is very simple, and you get an enhancement image. The thing is that from that enhancement image, we've got a detection, which, as I was saying before, can be based on a threshold or on automatic methods. For example, for UNEP IMEO, they have developed here in this example a whole algorithm that is based on machine learning and can automatically infer where you have the plume with quite a good successful results, because let's say manually is very, very difficult. We in the beginning, let's say we used to do that, but it came to a point where you've got hundreds or even thousands of plumes, and it's almost impossible. And then from the quantification level, we've got a quantification that actually takes this mask and converts into kilograms hours, which is the quantity we are looking for, and estimates how much methane is being released per hour. This quantification is based on transport simulation and is validated against in situ control relays. When I say in situ control relays, it's basically you go into a place with a big truck and you know exactly what you are releasing, and that's how we validate that what we are actually measuring. They don't tell us exactly what they are measuring and what they are releasing, and we just here you got an example of the validation we carry out with the guys from Stanford, and the results were quite successful for these initial algorithms. And yeah, so let's say few examples with Sentinel-2. So as I was saying, with Sentinel-2 might not be the best sensitivity for a mission, but the thing is, because it's there, it's 5-day revisit. It brings a lot of opportunities. And here you can see different examples like this. The one on the left is a plume in Copernicus, which is Turkmenistan, that you can see from an oil and gas rig. This other in the center is an example in Hassim Sud, which is in Algeria. It's another place we are monitoring. And the one on the right is a plume that we can find, for example, in the Permian Basin, which is an oil facilities in the US. So say this, that if you go, for example, to this webpage called methanedata.unep.org, you will find over 10,000 or more at the moment of detections with different satellites that they are continuously monitoring. Among them, many of them are with Sentinel-2. And what you will find is that they are monitoring absolutely everything, and it's expanding and expanding, and the capabilities are enormous. So said this, after all this basic introduction of the thing, I just wanted to show you that it's not so complex, and we are basically trying to do this with the help of these cloud platforms, because they are helping us a lot to automatize the process. So I just wanted you to, it's very simple, okay? But I just wanted to show you a very quick test. So if you want to do it by yourself, it's also possible. You can take a screenshot and try by yourself. We can make a quick test in the Copernicus data browser. I didn't do it in WEkEO because at the moment it's not possible to do a ratio of one directly, but I've been told that this will be possible in the near time, in the short time. So if you go to this center, like 38 north, 54 east, you can find an image like the one I'm showing you here, and you will be somewhere in Turkmenistan. You can select the Sentinel-2 Level 1C and press Show Latest Date. You can select a layer, which in this case will be a custom layer. You can create an index with the band 12 and the band 11, as you can see here, just dragging the band 12 and the band 11. And you can create a time lapse by pressing the icon you've got here on the right of the screen. So if you want to do it by yourself, as I said, you can take a screenshot and try by yourself. But here I've got the example just to show you that it's straightforward with this. And you should see something like this. If you see the image, this is a GIF of different days. What you must see in the center of the image is a plume that is actually coming out of an oil rig. I don't know if you appreciate here in the middle of it, and it's changing with the different wind through different days. So basically, this is done through the browser very quickly, but we've got the same. We are doing the same with the APIs, Python APIs that you can find on WEkEO, and it's very easy to implement at the detection level. Then we can quantify, but obviously for us at an operational level, it's very easy to have access to all these data sets online. And from this talk, I can say that as a summary, so methane mapping from space has been shown to be very useful to monitor and mitigate emissions, to actually bring all this satellite data into real action. We have seen that. We have seen the whole process in really few years. Sentinel-2 mission contains sensitive bands, and as I said, it's not the most sensitive mission, but it's playing a very important role in the development of a global monitoring strategy, because as soon as you've got an event, let's put an example. You've got a gasoduct that is broken, a pipe is broken somewhere. Is always Sentinel-2 is open and is there. Sentinel-2 and Landsat are there. So it's the first one that is always going to be there to monitor. So that's why it's so useful, because it's open and it's so easy, as I told you here, with a very simple example, you can go and monitor in a minute. So we can see that there is a retrieval method for Sentinel-2 based on a temporal band ratio of band 12 and band 11, so that the quantification can be based on a transport simulation and validated against in situ control releases. And importantly, as I said, you've got all these online platforms such as WEkEO, which are facilitating a lot the implementation of this at an operational level. And that's all.
Thanks a lot, Javier, for your presentation. And so we have a few questions for you, obviously, and we will go to that part. So I will wait till it's on the screen. So the first question being, how does spatial resolution of Sentinel-2 impact the accuracy of methane hotspot detection?
Yeah, I mean, the accuracy of methane hotspot detection, I mean, the sense, we call it sometimes the probability of detection or detection limit, it is typically a combination of the spatial resolution and the SNR. So the SNR of Sentinel-2 is acceptable, let's say. So you've got this problem, especially you've got two problems. Or challenges, let's call it that way. That one is that the SNR is not massively good, and especially the heterogeneity. So you can find many outliers because you are making a ratio of 2 bands. When you are using a whole hyperspectral, you can find less outliers, so it's much better and much easier to detect. But in general, very simple is the spatial resolution, the lower the better, combined with the SNR, the higher the better. Plus, the more bands, the better. It's a play of a game of thought.
Okay, thanks for the explanation. Okay. Sorry. What is the evolution of methane emission over time in the last 10 years? Did the sources vary?
Well, that is something I do not exactly. I've seen. Well, you can find the evolution at an absolute level of the methane, and it's always continuously rising. I think now it's 1900 parts per billion, so going from 17, 1800 parts per billion. Then there was sort of a hiatus like 10, 20 years ago, and then it ramped up again. There are many discussions about these sources, and at the moment, well, I can say that with methane mapping, we are trying to find out the sources which are more concentrated. We have started with oil rigs because they are a whole source coming out from a very hole, let's say a very tiny hole. So we've got everything concentrated. We are moving into landfills which are less concentrated, and we can move also now in. We also recently moved into palm oil that you can also find, but it's more difficult because the less concentrated they are, the more difficult it is to detect from a satellite. For example, the rice, which is one of them. So there are a lot of potential emissions, and the sources vary a lot. And there are even natural emissions like the one from termites, which are very well known, and wetlands, and so yeah, there are many sources.
Okay, thanks. The next question, does the plume detection algorithm yield any false positives?
Well, yes, it depends on the plume detection algorithm you are using, and it depends on what methodology you use. So, for example, what we are trying to do is, depending on the mission, you've got a lot of outliers, we call them. So in the image I was showing you before, you can find a plume, but you can find other things that are shown as plumes that they should not be a plume. Let's say, for example, a solar panel typically shows as a false positive. The thing is that we've got different strategies. So at the moment, for example, I would say that the best strategy is to use a machine learning, being very cautious, so it doesn't detect absolutely everything. It tries to detect the things, and then there is a human control over those. Like, for example, you need to make sure that the plume is going in the same direction as the wind, that is have this sort of expected plume shape and so on. So there are many things there. And yes, still there you can find false positives, of course, but they are rare after you have all these steps.
Okay, it's clear. Thanks. Next question, still about the plume. How are the limits of the plume decided in order to mask it properly?
So yeah, it is not a single rule, but let's say if we can put a rule of the thumb, is anything that is above 2 sigma of the noise of the enhancement of methane. You obtain a, let's say the most straightforward way is you get the image of methane enhancement. You assume a sparsity, therefore you calculate the standard deviation of that image, and over 2 sigma, you will say that this is what you are going to mask. That would be the straightforward way. But obviously, it's not so straightforward, so you can do it manually, and you can do, for example, if it's a machine learning algorithm, you can do with different other strategies. But the most important, I would say, is that whatever the method you mask, you calibrate. Let's say the same, you calibrate your flux rates with the same mask methodology that you are going to use in your operational case. So that would be the main ideas.
Okay, thanks. Another question. So I've read that Sentinel-2 with B11 and B12 isn't really suitable for methane detection. Maybe Sentinel-5P are better for that.
Yes, so well, there is no better or worse. As I was saying before, there are different possibilities. What you've got with Sentinel-5P, we use what is called a tier like layers. So you start, the way we detect things is like you start with Sentinel-5P tropomic, which goes into hotspots. Then you can move down to other missions, like let's say Sentinel-2, Landsat, and so on, and you can go down to another layer of, let's say, Mmap or so. And the different layers bring you different temporal revisits, bring you different spatial resolutions. So Sentinel-5P, for example, is much better in terms of, has almost daily coverage, has a very good spectral sampling at the 0.1, 0.2 nanometers or so in that area, which brings very good retrieval of the methane, but it's very difficult to be used for let's say for methane plumes, because they are at the scale of, let's say, hundreds of meters at the most, or 1 kilometer, whereas the Sentinel-5 pixel is, I think, is at the 8 kilometer or so. So what you find out is that it's not very sensitive to these methane emissions. So it's much better used for methane area mapping. So understanding the thing at the absolute level, whereas this Sentinel-2 and these other missions are much better at the relative level.
Okay, thanks for the explanation. The next question and the one after that are kind of the same. How scalable is this method to detect carbon emissions plumes? And also, has this been used for other purposes to track methane, like agriculture or farming? So, is there another use of the?
So do they mean CO2 emissions or?
Yeah, I guess so. Yeah.
So basically, we already do that. So we detect both plumes of methane and CO2, and also NO2. So this is happening. So it's actually with Sentinel-2, there's been a publication where it is possible to detect NO2. Again, not a very sensitive values, but they've been doing through power plants, for example, where you can monitor the NO2 emissions of power plants, large power plants. And for CO2, for example, we work on those kind of detections where it's very important, for example, the co-detection of CO2 and methane in flaring systems, because the flaring basically tries to burn the methane that is in excess, or they don't want to sell it. And we can convert that CO2 on the potential methane that is burned. And there is a part which is burned, there's another part which is not burned. So you've got methane and CO2 co-emitting. So yeah, let's say methane, CO2, and NO2 are something that is already happening.
Okay, thanks. Okay. And yeah, so does this method detect methane emissions over ocean?
Yeah. Actually, I would say we were the first ones to do that with a satellite over the ocean. It was in an oil rig in Mexico, which we found out with Worldview 3. And the difference between the ocean and the land is that basically in the ocean you've got a surface which is very dark, and the best way to find out is trying to go into mirror-like, into, let's say, no, I can, the mirror, how do you call it? Sorry, I forgot the name. So basically in mirror configuration where you will find the glint, sorry, the sun glint. I couldn't find the word. So if you go into the sun glint configuration, you will find a lot of radiance, and that's where you will be revealing the methane. But it's very important to also to monitor the methane emissions over the ocean, because many of these oil facilities are completely non-tracked. You cannot go there, and yeah, they are even more, how to say, unmonitored.
Okay. Well, thanks a lot for the presentation and the questions. We will have to stop there for the time we have. But yeah, thanks again for your participation and joining us today.
Thanks to you.
So we will go to the next use case presentation, which is by Ines from Collab Atlantic. Welcome, Ines, and you can start your presentation whenever you want.
Thank you. Hello, everyone. Good morning. We are very pleased to be here today to share our work on using Copernicus Earth observation data to support local scale climate services. So in this presentation, I will show you how we move from Copernicus data layers to producing local climate zones classifications, which are crucial climate informed for urban planning, risk assessment, and policy development. I will walk you through the problem we are addressing, the methodology actually developed by Ana Oliveira, and the tools we are building to make this process scalable and accessible at Plus Atlantic. So, a bit of who we are. This is not up. Now it's working. Thank you. So we are at Plus Atlantic is a Portuguese non-profit R&D and innovation institution. It was established around 19. It was founded to advance integrated knowledge on ocean, atmosphere, climate across the Atlantic. This would be done by delivering knowledge-driven products and services in blue economy, marine science, climate adaptation, coastal resilience, and ocean sustainability. Of course, while prioritizing technological solutions like Earth observation, numerical modeling, remote sensing, artificial intelligence. So now into the problem. As we know, cities are increasingly exposed to multiple compounding climate risks. So we are seeing extended summers adding up to 50 extra hot days per year, pushing around 70% of vulnerable households into energy poverty. We also see heat waves lasting 10 to 20 days annually, becoming more dangerous in cities where we see around 12% of the homes only having air conditioning. At the same time, we see prolonged droughts that are fueling wildfire risks, and we also see short bursts of intense rainfall that threaten thousands of people and buildings with flooding and sea level rise. But what I want to highlight here is that these climate impacts are not evenly distributed, so they can vary according to the physical structure of our environment. So the visual that you see on the bottom of the slide represents a gradient of built and natural surfaces, from dense high-rise blocks to open low-rise areas, and also green or water-covered landscapes. Above this visual, you have the color bars that show examples of key climate stresses such as temperature and NO2 concentrations varying across these environments. So as expected, we see compact urban forms that tend to trap more heat and accumulate more pollution, while vegetated open surfaces help mitigate both of them. So this is to illustrate how urban morphology directly shapes exposure. So to respond effectively, we need, of course, to have spatial detailed information that captures these structural differences, and that's exactly what Copernicus data can help us on building local climate zone type classifications. So, how do we build a solution that translates this EO data into meaningful localized climate intelligence? It starts, of course, with the input data. That can be cartography, including terrain models, administrative limits, infrastructure layers, observation, of course, using sensors and IoT to monitor real-time environmental conditions, and finally forecasting, which gives us context from the background climate trends and future climate scenarios. So these data streams are brought together through integration mechanisms such as artificial intelligence, spatial modeling, and the result is, of course, a layer of added intelligence, enabling more informed, spatial-aware decision-making, not just what and when, but critically where to intervene. So by combining LCZ classifications with other layers, as the ones I mentioned, we can deliver added value climate forecasts tailored to urban morphology. We can be more precise on risk assessment inputs, such as localized vulnerability to heat or pollution, and scenario tools to test planning strategies under different urban and climate futures. So this system-level approach would support cities in designing evidence-based, local-specific adaptation strategies. So now, what are LCZs and what do we need? To address the spatial differences of the climate risks, we need a framework that captures the physical characteristics, and that's where local climate zones come in. So LCZs classify the urban and natural landscape into standard types of dimensions. There are four. One of them is the height of the surface features like buildings and trees, the density or packing of those features, the surface cover surrounding them, such as concrete, vegetation, bare soil, and the thermal properties of the materials involved. This classification helps us understand how different parts of the city respond to different climate drivers. Continuing. Here you see a complete classification scheme of the local climate zones. This system was initially developed by Stewart and Oak. So they provide a standardized typology to describe the urban and natural environments, as I was saying. On the left, we have the build types ranging from compact high-rises areas like city centers with dense vertical constructions to lightweight or open low-rise structures found in suburban or informal settings. These categories reflect both morphology and material, which directly influence thermal and pollution dynamics. For example, how much heat is retained, or how air circulates, or how surface runoff behaves. On the right of the slide, we have the land cover types, including forested areas, shrublands, grasslands, bare surfaces, and water bodies. These natural types are equally important as they regulate many aspects of our environment, such as evapotranspiration, shading, air quality. And this is what makes LCZ powerful because of their global standardization that allow us to map and compare every urban environment if we use the same methodology. So into the workflow and what we actually did at PlusAtlantic. So of course, initially the workflow begins with the collect of input data. The base layers of this methodology are Urban Atlas and Core Inland Cover. Then we also have adding information, the tree cover density, the dominant leaf type, grasslands, and impervious density. We also have an optional layer we can use for the OpenStreetMaps to infer building height. Then we go into the pre-processing of the data, so harmonize everything, every data set with each other, merge it with the Urban Atlas and coordinate land cover, making it a baseline polygon layer. Then it's enriched by the high resolution attributes. So all of these inputs are reclassified using rule-based rules that allow us to infer where each classification goes. This is all done initially in Archie's toolbox. You can go into the paper that was provided in a website where this is all described. And you can see also that this was tested in 5 southern European cities, so Athens, Barcelona, Lisbon, Marseille, and Naples, and achieved 80% overall accuracy. Here in this diagram, we show how different land covers, so essentially the workflow of the reclassification. So the land cover and the land use data sets are combined and then reclassified into the LCZ categories. On the left side, you see the input layer, so primarily Urban Atlas codes. And in the middle, you see how these classes are enriched with the ancillary layers. So the grassland, tree cover density, OpenStreetMaps, to then refine the classification, particularly in areas with ambiguous or mixed type typologies. So on the right, these inputs flow into aggregated classes such as LCZ 1 to 3 for compact built-up areas. Then you have LCZ A to D for different types of vegetatious surfaces, LCD 10 for heavy industry, and then the other remaining classes. As an example, we have the first Urban Atlas class, which refers to continuous dense urban fabric, which is directly linked with LCZs 1 and 3, depending on the structural attributes like imperviousness and cheek cover. In contrast, the class 23000, it's easier for me to say like this, representing green areas, flows towards LCZ-D, linked with lowlands and managed grasslands. So this rules-based classification allows for a deterministic, scalable, and interpretable translation of Copernicus land products into the LCZs. We give you here some, as I said, I applied this to different cities because these are cities that are suffering of intensifying summer heat. They clearly differentiate, as you can see, compact urban cores, mixed-use areas, industrial zones, and this spatial detail allows us to analyze pattern of urban heat exposure, pollution hotspots, or green space deficits. I'll go and show you an example. So here we see a real application of the LCZs in Naples, where we explore the relationship between urban form and temperature during the day. On the right, you see an image of diurnal land surface temperature mapped with Landsat 8. And on the left, you see LCZ classification map that highlights the distribution of the built-in land cover types. The chart in the lower left plots of the diurnal surface urban heat intensity across LCZ types. It shows that you don't see a huge contrast during the day, but then when we look at the night picture, you see a much bigger contrast. So this is also reflected by the plot that you can see on the left. The reason essentially lies on the thermal inertia of the dense urban materials, so concrete, asphalt, that store heat during the day and then release slowly during the night. Now, to make LCZ mapping more accessible to everyone and operational, we are building a platform. This platform will allow users to generate LCZ classifications for any European region of interest through a graded interactive interface. So the first thing you need to do is defining a region of interest. You can interactively select an area by drawing, and in the future we want to also add the possibility of you inputting a shapefile or something that relates to the extent that you want to see classified. Here is just a brief overview of how the processing is done. So you can also ask for a specific type of output format, and the awaiting time, of course, will depend on the queue in size. Here is just an example of a classification done manually in ArcGIS and on our automatic platform. You see no major differences. So we were able to quickly solve it and automate the LCZ classifications. And also this was, of course, validated. And so the platform generates 50 reference points per class, selected through a stratified random approach. These points are then compared manually or referenced with LCZ labels, allowing us to compute common accuracy metrics, such as overall accuracy, that in this case yields a 90%, and kappa coefficient that in this case yields 96%. One interesting finding is that LCZ10, so heavy industry, constantly show the lowest classification confidence. So it's a tricky class to yield. So essentially what's next is to build a participatory WebGIS platform where users can make their own validation. They can gather more than 2 or 3 years of information, and is eventually create a machine learning algorithm to improve classification using supervised classification methods. And also the expansion of LCZ outside of Europe, because Copernicus allows us to do that. So this will be one of the next steps. Thank you very much. This is it.
Thanks a lot, Ines, for your presentation. So we will go to the Q&A session with Ines and Anna, so both of them. Okay, so the first question being, is your data applicable to any cities globally or European cities only?
I guess that this last slide answered this question. Essentially now we can do it for Europe, but we are developing to make it possible globally. Yes.
Okay, thanks. Next question, do you have information about vegetation quality? Same question for substrate Q.
Not in this workflow. We don't consider the vegetation quality, although we do consider types of vegetation, not the quality.
Okay. The next question, is the classification pixel-based or object-based?
So when we are computing some of the classifications, we use area-based. Although we are working with pixel-based, so rasters, we do use areas to compute this information, because if we were using only pixels, we would yield 100% of everything in each pixel. So we need to consider a bigger area to compute the statistics. Yes.
Okay, thanks. Makes sense. Up to the next question. Could these urban atlases be processed also with QGIS?
Well, so Ana Oliveira developed this in ArcGIS. I believe that because of that, you are able to implement the workflow in QGIS, although I believe that would take you a bit more and would be processing heavy.
Okay. Okay, thanks. The next question, so is it possible to compare the same area between two different periods, for example, after 2 weeks of dry and warm season versus 2 days after 60 millimeter day precipitation?
Okay, so this workflow and the local climate zones are computed based on yearly inputs. So you of course can compare it, but you will be using time fixed information. So for that year. So if you compute LCZs for different years, you could then make different comparisons. But in this case, it's a yearly timed fix, let's say. I don't know, Anna, if you want to add anything to this. Feel free.
Do you have any idea of much time it will take to launch globally?
Not for sure. We are working on this. We are starting to work on this, and I would believe that maybe next year we will have it operational and public available.
Okay, thanks. Thanks for the precision. Okay. What is your reference data set for accuracy assessment?
I would
Ines,
say,
maybe I
yeah.
get this one.
Yes, please.
So because this one is actually done back in 2019. So for reference accuracy assessment on the original methodology, we selected random points and we visually inspected the site. So it was manually inspecting site by site in terms of the actually local climate zones. Concerning the platform in itself, it's different. So because the idea is for the open platform to replicate the original method, so the target reference data set is the previously published LCZ maps that you can find in the original papers. So it's different. You have all the details of this and the published materials, and yeah.
Okay, thanks. Oh, and another question, can QGIS tools on WEkEO help in mapping local species or habitat zone? So concerning the tools available on WEkEO, you can try to do that on your side. I don't know concerning your project, Anna and Ines, if it could be like kind of replicate to another like the question, so for species or habitat zone, can you think you could use your project to yeah?
Should I answer, Anna? Will you? Yeah. So, well, in the concept of local climate zones, of course, it would be since I'm a scientist, it would be very curious to compare with species or habitat zones. Of course, it could have added value, but I don't know at which point it will give you input on habitat or species, because this also considers urban areas. So I would say that you would need to input other information to be able to map local species or habitat zones. But for sure would be an added value classification, yes.
Okay, thanks a lot. That's it for the question for your presentation. So thanks again to both of us for joining us. And yeah, now we will go to the last user testimony of the day. And welcome, David. Hi.
Hi, good morning. Thank you very much for the kind invitation. Okay, so today I'm gonna discuss with you our tool, Climameter, that is a tool to perform rapid attribution to climate change. And Climameter is based on Copernicus data, so it's a pleasure for me to present it in this situation. So I will first start and let's see if I can move forward the presentation for the moment. Yes, here it is. So let's start to say what is Climameter. Climameter is many things, but is first of all a consortium of international scientists that are all over the world. At that time, happy to coordinate from the CNRS in Paris. And the goal of our consortium is to perform attribution to climate change of extreme events that have happened in a very timely manner. In fact, what we aim to is to have our reports ready in 24 to 48 hours after the event. And in fact, as you can see, if you navigate in the website, and you will have a QR code to reach the website at the end of the presentation, you will see that our last event that we have covered is the fire in Canada that is ongoing. So sometimes we also have ongoing events. And for the moment, we have over 70 events. And the idea of having these attribution reports ready in short time is that we can communicate to the international press. For the moment, we have hit over 2,000 international press articles. Sometimes it's difficult to estimate the right impact for our reports, because what happens is that some press agencies such as Reuters, AFP, or ANSA, they take our reports, and then the newspaper publish the results in cascade. And so we have many times the same kind of articles that appear in different journals. So for this presentation, I start from the results. You can see here a map of the events that we have covered so far. We have a global coverage, although we would like to strengthen our coverage in the global south. And you can see different colors that corresponds to the different kind of events that we cover in Climameter. The light blue is related to windstorm. The blue is related to floods. Then we have violet that is related to cold waves. We have yellow for heat waves, and we have red, although you cannot see them here, for fires. And the output that Climameter provide is how we can attribute an event to climate change. So you can see that for about 15 events, we have that the events have been strengthened by climate change, or likely strengthened for climate change for 30 events. And then we have an interplay of natural climate variability and climate change for about 30 events, and just 3 of the events that we have analyzed out of these 70s are not linkable directly to anthropogenic greenhouse gases emissions. So we see that in most of the events that we have analyzed, we can really detect an influence of anthropogenic climate change on the events. And another output that Climameter provide is the rarity of the event. Most of the events are very exceptional, which means that we don't have other events that look like the ones that we want to attribute in our dataset. And this is also interesting because the rarity of the event allows us to put score of confidence on the kind of analysis that we provide. So given all these results, how do we perform our studies? First of all, I want to recall what is attribution. Attribution is linking an event that produced some impact on health, infrastructure, property, tourism, agriculture to the sources that can be greenhouse gases emissions or the natural climate variability. So these impacts are produced by climatic hazard. For example, if we have strong winds, we can have damages in the infrastructure. If we have heat, we can have impact on the health or on the tourism, and so on and so forth. So the idea is that this climatic hazard can be, of course, directly analyzed by looking at the time series of the hazard themselves. But in climate meter, what we do is that we link this hazard to their origin, that is the weather phenomena that is producing the hazard and then the impact. For example, a cyclone can produce at the same time wind and rain hazard. And therefore, by looking at the level of the weather phenomena, we can at the same time attribute to greenhouse gases emission or climate variability of an interplay of the two several hazards at the same time. So that's the goal of climate meter, and also why it is different from other attribution methodologies that instead are based on looking at directly at the hazard. Looking directly at the hazard, for example, if we consider rain, can be sometimes misleading because rain can be produced by very different phenomena in the weather. We can have rain because of thunderstorm, that is a very small scale phenomena, or we can have rain because of large scale synoptic meteorological structures such as tropical or extratropical cyclones. So going to this level allow us to really understand the physics that is leading to some change because of greenhouse gases emissions or natural climate variability of some hazard. So how do we do? As I was saying, we use Copernicus data from 1950 to present, and what we look at to being able to detect changes in our events is the large-scale pressure structure in a longitude-latitude box that fits our event. And the method is very simple because it's based on analogs of this pressure pattern that we have defined as a long latitude box containing the event. And therefore, what we do is that we assess difference present versus past analogs, having the hypothesis that the past is barely affected by climate change and the present is highly affected by climate change. By looking at the difference between pressure maps associated with the analogs, we can also look in cascade to the different hazards during these analogs. So, of course, pressure, but also temperature, precipitation, winds, or other impacts variable. And of course, just looking at statistical changes will not allow for attribution because we have to include or exclude the role of natural variability that we do by looking at the main modes of natural variability such as El Niño Southern Oscillation, ENSO, AMO that is Atlantic Multidecadal Oscillation, or PDO that is Pacific Decadal Oscillation. The best way to understand climate meter is through an example. So I will show you here very briefly the storm Eowyn. That is it's an explosive storm, an extratropical cyclone that hit the British Isles and France recently. And basically we had a drop of 50 hectopascal in 24 hours, a pressure minimum of 940 hectopascal, extreme winds above 130 kilometers per hour, and many impacts, especially on the property damages and the energy sector. So how does a climameter work? We do an analog search. So you can see here for the top left panel, the sea level pressure anomaly. That is what we look in terms of analog for the storm Eowyn that occurred the 24th of January 2025. So we select about 30 analogs in the past period, that for us is 1950-1986. We select the same number of analogs in the present period, that for us is 1987-2023 for this storm. And then you can see that the last column is the delta, that is present minus past. And this delta shows that storm similar to Eowyn have intensified in terms of having a deeper pressure minimum in the present compared to the past. And we also see that there is a positive pressure anomaly over the continental Europe, and therefore we have a stronger dipole of pressure. So let's see what this implies in terms of temperature. First, we can see the temperature during Eowyn, still this left plot. Again, we have the past and the present temperature during the analogs of pressure, and then we can see that the temperature is generally higher, up to 3 degrees warmer in the present compared to the past on the British Isles and North France, the Benelux and Germany, while we have a lower pressure because of the deeper pressure gradients here. And we can see that we also have higher precipitation in Scotland and in the English Channel, and we can have stronger winds. So that's basically the methodology. We can also detect whether the event is rare compared to the analogs. So here I show you two distributions. The blue distribution is in terms of the violin plot, the distance from the analogs, from their analogs for the past and the present, compared to the blue dots, that is the distance of the event, so storm Eowyn, compared to these analogs. As you can see, if the blue dots, like here, is inside the distribution, we can see that this event is not exceptional, so we have good analogs, and therefore we have high confidence on the kind of results that we have produced. We have robustness on the methodology that has been explored in the work that you see cited here. And similarly, having the dates of the analogs for the past and the present, we can look how the El Niño Southern Oscillation, the Atlantic Multidecadal Oscillation, and the Pacific Decadal Oscillation could have influenced the event. So you can see here that we have the shift between the distribution of the past, again in blue, and the present analogs during for the different indices, and in this case only the Atlantic Multidecadal Oscillation has a significant shift according to a Kramer-Formises test, and therefore we cannot rule out that the changes that we see and that we have commented before can happen because of a different phase of the Atlantic Multidecadal Oscillation. So we summarize all these results in the kind of output that you can see in the Climameter website. So the role of the natural variability is basically expressed from the first meter here, that for every mode of variability that is significantly different with present with respect to the past, we go from strengthened to climate change to influenced by natural variability. And the assessment of the rarity is what you see in the second meter, where you can see that our event is not rare, but it's not even very exceptional. It's somewhere in between, given our analysis of the distance from the analogs. The plots are always presented in the same way. They contain again the results that I shown. So the first row this time is for the event themselves. We have pressure, temperature, precipitation, and wind during the event. And the second row is the changes that I have already commented with, showing deeper pressure, higher temperature, stronger precipitation, and wind speed increased. So we give all of this to the press. So with the summary that you can find for each of our events and contain 3 items. The title show that the event has been strengthened by climate change. Then we have an item that tell us how changes translate in terms of pressure, winds and precipitation, the rarity of the events, and the attribution statement that in this case says that we mostly attribute the increased powerful storm of Eowyn to anthropogenic climate change. So the key features of Climameter from this first example that I show you is that we are fast, we can link the events with the meteorological conditions, and we have a physical interpretability of the change that we have commented, because like in the case of Eowyn, we have deeper pressure that entrains changes in terms of wind and precipitation. And of course, the other things that is our also working platform for the moment is that we want to include climate models for the future. I finish with some references, and I thank you very much for your attention. You also find here a QR code that will drive you through the website, and of course you can write us to give us feedback, and I'm very happy to answer the questions that you may have about Climameter. Thank you very much.
Thank you, David, for your presentation. It was really interesting, and we have a few questions for you. So I will just wait till it appears on the screen. The first one, so interesting presentation. I will be glad to provide inputs over West Africa. Is it possible to join your team?
Yes, of course. So if you basically write an email to the email that you've seen before, or the contact that you have on the website, our consortium is open to the colleagues. So if you want to join, we are very happy that you join. And we're also realizing a study on the last 30 events on Africa in the last 5 years with African scientists, because we've seen that we have this weakness that we struggle to cover events in this continent, and therefore we will be very happy if we strengthen the African team of colleagues and in general the global south with more colleagues coming from these areas.
Okay, good to know. Thanks a lot. So yeah, the presentation will be made available in a few hours, so you will be able to see the contacts and everything. Thanks a lot. The next question: could you study other events with Climameter?
So yes, we can study other events, and we have some peer-reviewed materials that extend our study, for example, to the dust storm that we had in Europe in 2024, and that we have continuously. And so with the analogs approach that I showed, we have analyzed the dust storms that occurred at Easter time in 2024 in Europe. And we are extending the methodology also to cover convective events, large-scale outbreak. So I have a paper in collaboration with Columbia on the tornadoes outbreak in the US that can start to be covered with this methodology. And I'm working now at covering hailstorm, like the hailstorm that we had in France in May 2025. And the methodology is versatile, because once you have this link with large-scale conditions and hazard, you can apply the methodology to other class of events.
Okay, thanks a lot for the explanation. So we will go to the next question. Is there an area or areas where these hazards concentrate more?
Bad news. Thanks for this question, but I mean, we have currently hazards everywhere in the world. So of course there is a different vulnerability of different areas. For example, tropical areas are more vulnerable to floods, heat, but humid heat, and tropical cyclones. And instead the mid latitudes are vulnerable to fires, to extreme heat, to floods, to extratropical cyclones, and to thunderstorm. And therefore, we have different hazard in different areas. But for the moment, we receive every week requests to cover hazard all over the world. So, and this it's not expected to get better unless we reduce the CO2 emissions.
Yeah, exactly. Thanks a lot for the answer. So thank you. You mentioned using ocean pressure data from the 50s. Which are they based on?
These are definitely thanks for the question, Copernicus data. So we use ERA5 and we trust, so all our methodology is based on the fact that we trust ERA5 reanalysis, and there are many studies that say that we can trust ERA5 reanalysis for these large-scale fields such as pressure, temperature, precipitation, and wind. And the thing is, we also used in the past other dataset to compare, for example, NCEP reanalysis, but which are at a lower resolution. So the power of ERA5 is that we can really go to the 25-kilometer scale. That is the one that is relevant for large cities, for distinguish the topography, and this is really the advantage of using this kind of reanalysis.
Okay, thanks a lot. So the next question, how does spatial scale accuracy affect the reliability of climameter results? Does it provide better insights at a global or regional level?
Thank you for this question. So climameter, as you can see from the example, we have to cut a certain area that fits our meteorological structure to perform the analog search. So it performs better at the regional level. If we extend the domain and we take a domain that is too large, then we will fit more than one cyclone, more than one anticyclone, and in that case, the analog's quality will lower. So the best practice is to fit the structure that we want to attribute. It is the one that is producing the hazard, which means that there is a lot of expert judgment with this climameter. And the other problem is that if we take the area too small, then we don't have a cyclone and anticyclone, we have just few grid points, and in that case as well we can have problems. So there is an in-between that is the good structure that fits our synoptic conditions that is producing the hazard.
Okay, thanks for the explanation. I think it's clear now. The next question is a tricky question. How climameter is better than any other climate tools for global data management of climate change?
So I would say that climameter I will reinterpret the questions, and thanks for this question, as compared with other attribution framework that have the same goal. So in fact, there is the advantages of climameter with respect to the other methodologies to have this physical interpretability of the changes, because we have at the same time all the hazards and we link them to the meteorological conditions that produce them. But it doesn't mean that other methodologies that are based at looking, for example, at changes in the hazard are not useful. For example, the World Weather Attribution, that is the other consortium producing attribution studies with the statistical methodology, it has also a very important component that is linked to the vulnerability and the exposure of the population to the disasters, and that part is not in climameter, but it's really, really useful because it links immediately the changes to the populations that is affected by certain hazards. So there is collaboration between climameter and all the other consortia that realize attribution studies, and this is very nice. In our community, our goal is also to provide timely information to the population, and this is the goal of the attribution community. And although we have different methodologies, we have this common goal, and we discuss a lot among each other on how to reach this.
Okay, thanks a lot. So we have still time for a few more questions. How do climate variability models from CNRS help in predicting future threats to endemic species in vulnerable regions? So I don't know if you know that, but
Okay, so this can be, for the moment, we are not doing this because attribution is present versus past. But of course, the same methodology of the analogs, we can produce a study on projections. We have to define warming levels. We have to define models. For example, yes, we have a IPSL model, that is a model the CNRS is participating, and project this in the future, right? But for the moment, we have not done it. We can foresee how to do it, but this is also part of the things that we are currently developing in my team here at CNRS, and not for these specific studies, but yeah, definitely you can use the analogs for also doing projection.
okay, thanks a lot. Another question. Do you think we can study permafrost degradation with climate meter?
Again, the climate meter approach, it's more broadly the analogs approach. Yes, you can study other phenomena on longer time scale, but then you have to change data set. For example, for the permafrost, I guess you have to use longer reanalysis and also models that can take into account the dynamics of the permafrost. And then you have to come up with a good observable for which you have to compute the analogs. Of course, it cannot be sea level pressure. So you have to adapt the methodology, but definitely you can do it.
Okay, thanks a lot. Okay, so we have time for a few more questions, but I think we will stop after the 3 we have. Does climate meter allow for near real-time operational services of any event which local meteorological service defines as extreme weather event?
So, in some sense, we can cover globally the event that come up, provided that they are in the events that we can cover, that for the moment are heat waves, cold spells, floods, cyclones, and fires. So we are working at the extensions to other events, such as I was telling, the convective hazards, tornadoes, hailstorm, but these are experimental for the moment, and we have to wait that these studies are peer-reviewed and published so that we can make a new version of our protocols that take into account also the new hazard.
Okay, thanks. And so next question. So is climate meter a Python framework? And if yes, what is the input and what kind of output can it give?
Okay, so climate meter for the moment runs in MATLAB and in Python. And for the output you have seen, the output is exactly the figures that I was showing. That shows you the 2 meters, the hazards during the event, and the changes present minus past. As input, what we have to give is simply the long latitude box for the event, the dates of the event, and 3 cities that are in a World Cities database, and that are the cities where we want to study more in details the changes. So these are basically, but the code is not in the nature. Why? Because of this problem of the expert judgment. So if we prefer to have the control of the studies that come up, because if a too narrow region is selected to perform the climate meter analysis, then you can end up with changes that go in all the directions because you are not constraining the right way to the circulation. And we want to avoid that, like people who are not trained to properly use these methodologies can release studies that are not scientifically grounded in what we know from the meteorology.
Okay, thanks a lot. And so we will go to the last question, a more open question. So do you think thermal front parameter and frontal diagnostic parameter variabilities got also stronger recently, maybe as a root causes for extremes?
So what we see in the climate meter studies is that there is in all the studies the thermodynamic components, that is the fact that we have warmer conditions that drives not only heat waves or decrease in cold, but also the precipitation. So we know that for each degrees of warming, we have 7% more rain in the system, the weather system that we have. But in climate meter, we also see that, as I showed for the storm Ewing, that was my example, we have increase in, we have dynamical changes. So cyclones that are getting deeper, that produce changes in weather patterns, and sometimes more precipitation in some area and less in some other area. So yes, the thermodynamics component is getting stronger and is the main route for extremes, but climate meter also tell us that we don't have to forget that also the dynamics and so the meteorology of the event is changing, and this drive additional changes that can be the catastrophic ones for which you are not prepared.
Okay, well, thanks a lot for the explanation. So
Thank
we
you
are
very
reaching
much again
the
for
end
the
of the
invitation.
question. So yeah, thanks again for your participation and the presentation. It was really nice. So we are reaching the end of today's session. So thanks again to everyone for their presentation and to you, the participant, for your participation. Before you leave, I just want to remind you that there is a section on the website next to the Q&A, which is reserved to the polls. So we would really appreciate to have your feedback on today and what we could provide in the future. So please take 2 minutes of your time to answer it. And yeah, so also, just so you know, sorry. The practical session with the tutorials will be the day after tomorrow. So the tutorials are not available yet because we have a technical issue on the website, but you will be notified by email once they are available, and you will be able to check the tutorials and to practice if you want. So they will be available in full with the video tutorials, and all of the tutorials are using Copernicus data available on WEkEO. And yeah, you will be able to download the tutorials, practice, and ask your question on day 2, where the experts will present the tutorials to you, and you will have some time allocated for your questions. So thanks again to everyone for joining us today, and see you in today's time. Bye.